Welcome to the second part of our tutorial, Trigonometry Demystified. Previously, we defined three trigonometric functions. For a right triangle with an angle alpha, the sine of the angle is defined as the ratio opposite over hypotenuse. The cosine is the ratio adjacent over hypotenuse, and the tangent is the ratio opposite over adjacent. In the following, we are going to see how these ratios can be related to the value of the angle. In other words, if we know the value of the angle, how can we predict the values of the ratios? Or if we know the value of a given ratio, how can we predict the value of the angle? Before we start, note that the present definitions imply that alpha is an acute angle, meaning that it is less than 90 degrees. Indeed, for any triangle, the sum of the three angles must be equal to 180 degrees. Since a right triangle has a 90-degree angle, alpha must necessarily be less than 90 degrees. However, in the following, we are going to see how these definitions can be extended to any angle. To begin, let us derive two important formulas that will be useful. Starting from the definition of the tangent, we can divide both the numerator and the denominator by the hypotenuse without changing the resulting ratio. We can recognize now the ratio between the definition of the sine and the definition of the cosine. Therefore, tangent alpha is equal to sine alpha divided by cosine alpha. A second formula is easily obtained from the Pythagorean Theorem. Adjacent square plus opposite square equals hypotenuse square. The equation remains valid if we divide it by the hypotenuse square. But now we can identify the first term as the square of cosine alpha and the second term as the square of sine alpha. The right-hand side simplifies to 1. It follows that for any angle alpha, cosine square plus sine square is always equal to 1. This means that if we know the sine of an angle, we automatically know its cosine. And we also automatically know its tangent, since tangent is just the ratio sine over cosine. We are now ready to analyze the relationships between the angle's value and the values of its sine, cosine, and tangent. For this purpose, it is convenient to consider Cartesian x and y coordinates with the so-called unit circle at the origin. By definition, the radius of this circle is 1 unit length. Let us take a random point on the circle. The distance between this point and the origin is a radius length of 1 unit. Let us call alpha the angle between the x-axis and the point's radius. The x-coordinate of this point is obtained by drawing from it a vertical line that intersects the x-axis. In a similar way, the y-coordinate is obtained by drawing from the point a horizontal line that intersects the y-axis. But now look what we have. We have a right triangle with a hypotenuse of length 1, an adjacent side whose length is equal to the x-coordinate of the point, and an opposite side whose length is equal to the y-coordinate. By definition, the ratio adjacent over hypotenuse is the cosine of alpha. But since the hypotenuse is equal to 1, this ratio is simply equal to the adjacent side's length. Thus, the adjacent side's length is equal to the cosine of alpha. Likewise, the ratio opposite of the hypotenuse is the sine of alpha, but since the hypotenuse is equal to 1, this ratio is simply equal to the opposite side's length. As a result, the opposite side's length is equal to the sine of alpha. So the advantage of using a unit circle and a right triangle with a hypotenuse of 1 unit length is that we have a direct visualization of the sine and cosine of alpha. What about the tangent? Once again, the tangent of alpha is the ratio opposite over adjacent. But for angle alpha, neither the opposite side nor the adjacent side has a length of 1 unit, so the ratio does not simplify. But here we can take advantage of similar triangles in order to obtain a direct visualization of the tangent of alpha. Let us resize our right triangle so that the adjacent side of the new triangle has a length of 1 unit. Since the angle alpha is not changed by this operation, the tangent of the angle is unchanged as well. But now the ratio is just equal to the new opposite side's length. So this length is equal to the tangent of alpha. To summarize, the cosine and sine of alpha are obtained by taking the x and y coordinates of the point, and the tangent of alpha is constructed by prolongating the hypotenuse until it intersects the vertical line that is tangent to the circle. Now we can directly see our three trigonometric functions on the figure, and we can start relating their values to the value of the angle. Let us write in a corner the two formulas that we just derived, as they are going to be very helpful. Let us start by decreasing the angle down to 0 degree and look at what happens to the trigonometric functions. The blue segment reaches a maximum length of 1, while the red and purple segments both go to a 0 length. We conclude that for an angle of 0 degree, the sine is 0, the cosine is 1, and the tangent is 0. Note that these values agree with our two formulas. For the first one, the square of the cosine is 1, the square of the sine is 0, so the sum is equal to 1. For the second one, the ratio sine over cosine is 0 over 1, so it is indeed equal to 0. Let us now open the angle to 30 degrees. In order to determine the value of the sine, consider the green triangle. The angle that touches the center of the circle and the angle alpha are complementary, meaning that their sum adds up to 90 degrees. Thus, the former must have a value of 60 degrees. Note that the two sides of the green triangle that touch the origin must have the same length, since each of them is a radius of the circle. So, this triangle is isosceles, which implies that the two unlabeled angles are equal. But their values must add up to 120 degrees, since the sum of the three angles must be 180 degrees. We conclude that this triangle has three angles of 60 degrees and is therefore equilateral. This means that the horizontal line drawn from the turquoise point cuts the vertical side of the triangle into equal parts. We conclude that the sine is exactly equal to 1/2. In order to determine the value of the cosine, we can make use of the first formula. Cosine square must be equal to 1 minus sine square. Sine square is 1/4, thus cosine square is 3/4. As a result, the cosine is equal to the square root of 3 over 2. Finally, by plugging the values of the sine and the cosine into the second formula, we obtain the value of the tangent. We obtain 1 over square root of 3. Let us now increase the angle to 45 degrees. The right angle having a value of 90 degrees, we conclude that the third angle in our right triangle must measure 45 degrees too. This right triangle is therefore isosceles, which implies that the blue and red segments have the same length. Thus, the sine is equal to the cosine. We can therefore substitute sine in place of the cosine in the first formula, which tells us that 2 times sine square equals 1. It follows that sine square is 1/2, and therefore the sine is 1 over square root of 2. And so is the cosine. This implies that the tangent is 1. Now, look at what happens to the tangent if we increase the angle's value to 60 degrees. it grows very fast. At this point, we can think faster and reuse what we already know. You can convince yourself that the present situation where alpha is 60 degrees is symmetrical to the situation where alpha was 30 degrees if we exchange the roles of the sine and the cosine. This means that cosine 60 equals sine 30 and sine 60 equals cosine 30. So, we can conclude that cosine 60 is 1/2 and sine 60 is square root of 3/2. Therefore, tangent 60 is square root of 3. If we keep increasing the angle to 90 degrees, the tangent goes out of the figure. The green segment becomes parallel to the purple segment, which means that the intersection of the two lines containing those segments is sent to infinity. That's where the tangent is. The tangent is infinite. Also, this situation where alpha equals 90 is symmetrical to the situation where alpha equals 0 if we exchange the sine and the cosine. We conclude that sine 90 equals 1 and cosine 90 equals 0. The ratio 1/0 also confirms that the tangent is infinite. Let us increase slightly the angle and look at what happens to the tangent. It suddenly jumped from positive infinity to negative infinity. Notice that now the angle is no longer acute, but the cosine has a negative value. This observation provides us an extension of the previous definitions of the trigonometric functions by adopting the following convention. For angles greater than 90 degrees but smaller than 270 degrees, the adjacent side's length is to be counted negatively. And for angles greater than 180 degrees but smaller than 360 degrees, the opposite side is to be counted negatively. The hypotenuse remains positive for all angles. We are ready now to determine the values of the trigonometric functions for an angle of 120 degrees. This case is symmetrical to the case where the angle was 60 degrees, except that the cosine is now negative. As a result, the sine is square root of 3/2, the cosine is minus 1/2, and the tangent is minus square root of 3. Increasing the angle's value to 135 degrees, we obtain a situation that is symmetrical to the case with alpha equals 45 degrees. Thus, the sine is square root of 2/2, the cosine is minus square root of 2/2, and the tangent is minus 1. For an angle of 150 degrees, you can easily find out that the sine is 1/2, the cosine is minus square root of 3/2, and the tangent is minus 1 over square root of 3. For 180 degrees, the angle is flat and the sine is 0, the cosine minus 1, and the tangent 0. Okay, I guess you got the idea. We can now move faster. For an angle of 210 degrees, the sine becomes negative and the tangent is back to positive. I'll let you check that we obtain the following values. For 270 degrees, the sine reaches its minimum value of minus 1, the cosine is 0 and the tangent is infinite. For 315 degrees, the tangent jumps again to negative values and we get these values. Finally, for 360 degrees, we are back to the same situation as for 0 degrees. Here is again a full revolution of the point without interruption, so that you can get familiar with these trigonometric functions. Notice that the tangent comes back to its initial value when the angle reaches 180 degrees. This means that the tangent is a periodic function and its period is 180 degrees. The sine and the cosine go back to their initial values after a full revolution, so they are periodic functions with a period of 360 degrees. To conclude this second part of our tutorial, we have seen how the values of the trigonometric functions can be determined for some particular angles. In the next part, we will see how the trigonometric functions can be calculated to arbitrary precision for any angle, and we will define 3 additional trigonometric functions.